Ziria in one thread. This is Ziria in two threads. I didn't describe the multi-threading model. It's just a top-level pipeline, coarse-grained multi-threading model. And we see that we are well above the requirements of the protocol, which is 40 mega samples per second. A sample is a 32-bit integer. And we are comparable to Sora, the manual code in one thread, but probably the Sora with two threads would be even much faster. So that's what I mean when I say it's blazingly fast. Now, on the TX, things are not so cool. So the TX works on pipelines of bits. So to optimize it, you have to be really very careful with how you pack bits and how you create lookup tables, because you're using loops a lot and you're using caches a lot. So the protocol rates are here. The dark thing, there's the requirements. Our code is here. Is the second guy in one thread. We see that in all rates, except maybe even from the final ones, we achieve the protocol requirements. So we're very close to protocol requirements. Two threads actually did not give us so much performance in the TX because of the extra overhead of queues and the bits. I'm not entirely certain what's going on there. But you can see that Sora is blazingly fast. It's like in one thread, as the rates go higher, it really increases. So I believe this is because of the manual provision of lookup tables and very careful design of where exactly you should put a lookup table and how big and how you're going to break up your computation. Whereas we are pretty dumb. Every computation that can be compiled to a lookup table, we'll do it. With no other extra model. So there's more work to be done here, clearly. I want to just mention the effects of the optimization. So for the receiver, all of the optimization is coming from the vectorization, or most of it. These are the effects from the optimization. The green are the effects from the vectorization, and the yellow is the effect of all optimizations. And the reason is because he operates on complex numbers, so by passing arrays of complex numbers, we already get like the big benefit. And it is big benefit. It's like 10 times more, or more than that. On the TX side, vectorization alone doesn't do anything. Because, okay, we create like tight for loops, but we still have to perform the computation for these for loops, so it doesn't do a lot. It does in some cases. But in combination with lookup table compilation, which is the yellow parts, we get huge performance benefits, even like 100 times faster. Okay, so there are some numbers about latency that I'm going to skip over. I just want to mention that by and large, we satisfy the latency requirements of the protocols, of the Wi-Fi requirements. I would just want to say that mostly latency requirements are satisfied. On top of this, the hardware amortizes the latency because the hardware has itself some buffers. You might think that because you're in software, you're more unstable and prone to jitter and latency issues, but the hardware buffers help with that. And the proof of this is that we see 95 successful packet reception that talks about MAC acknowledgement. So. So what's next? We're working on compilation to FPGAs and custom DSPs. We need a more general story for parallelism with many low-power cores, not just two expensive high-power cores. High-level semantics in a process calculus, porting to other hardware platforms, USRP, and if people are familiar with USRP and want help with that, please. Improve array representations, take ideas from Feldspars and Nicola. I think it's a good idea to work on a Haskell embedding to take advantage of generative programming or meta programming, the style of Feldspar and Spiral. And the conclusions is that I want you to take here is that although Ziria is not a pure functional programming language, the components are kind of pure from the outside, but the implementation is imperative. It has a design inspired by monads and arrows, so monads and arrows in action. It has stateful components that communicate only through these explicit channels, and that's a lesson from what are good ways to tame state in pure functional languages. It has strong types that capture the interface very precisely, the data interface and the control interface, and they allow for optimizations, like type-directed optimizations, that would otherwise be entirely manual, like vectorization, and harder to check. So, no, let us put functional programming ideas to work. We'll encourage more of that, and with that, I would like to thank you.
We have a few minutes for questions.
So I'm wondering how vectorization interacts with stream fusion. If I imagine that a component just doesn't take and emit,
then vectorization will introduce a loop in that component.
Yes,
file.
yes, 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 yes.
So if you have two of those and we fuse them together,
Ah.
bearing in mind that everything is inside an outer loop,
Yeah, yeah, got
it
it.
looks
got
as
you.
though
Because-
unvectorized, the loops fuse, but if you vectorize, you lose.
I see.
Fusion.
Yeah, that's a good point. But yeah, so I mean, very very good point. Hopefully, we'll be able to convert the two components into maps, and hopefully the two maps are going to be fused together. I mean, they are fused together, but we don't actually yet fuse the loops inside the map. So it's a very good idea for improving this even more.
So does that mean vectorization sometimes makes performance worse?
It might. We haven't observed this. That's why it totally makes sense what you say. We haven't observed this in practice, but I think I should investigate a little bit more on this. Yes, there's a very good chance. Yeah.
So you have these two-dimensional models, data and control channels.
Yeah.
Have you thought about extending it to more dimensions? You know, for example, you know, you can treat the data as a control channel output as a data channel input, and also do the same switches.
I haven't thought of this. If you have good applications where this would be,
Probably not practical, but best for conceptually completely.
might be interesting. If you want to go that direction, Haskell pipes is like it's kind of the category theory inspired multidimensional thing that you should try to extend. Yeah.
So Sora seems to be sort of the benchmark here to beat.
Yes. Yes.
They're very fast. So I wonder what you would do to get there, and in particular the kind of design choices you made in the language, whether you kind of some of them hinders you to get there.
So I feel that the thing that hinders me the most is the reason we were able to go as fast as now is because we took the Sora code and we tried to identify what people have been implementing manually and trying to make sure that our abstractions and our compiler can do these things automatically. But we clearly have not done a very good job yet for the lookup tables, I think. So I think I feel that the abstractions are reasonable at the moment in terms of performance. In terms of programmability, we discussed this. We might need something more for parallelism. But what needs to be done is sit down for 3 months through the Sora code and look exactly of what is the cost model that they have in their mind when they're implementing the lookup tables, and try to incorporate that cost model into our optimizer. I think that's my yeah.
Do you have any sort of measure of the relative engineering effort that went into building the implementation of Sora versus in your DSL?
You mean the implementation of Wi-Fi, not the,
Yes, so not actually building your DSL, but actually...
So I have anecdotal evidence from my collaborator who's a systems person, and he's been building these things, and he I don't know if I can quantify this, but I think it's a few months work for doing this in our language, whereas I think it was more than a year for many people. Well, so probably many man-years, like for the Sora guys when they did it. Of course, they were inventing everything, right? So and we kind of copied some of their stuff in the compiler when we did it, so the programmer didn't have to worry about it. So it's a bit of a strange comparison, a difficult comparison to make. Because, for instance, there's this amazingly clever permutation primitive, where kind of to permute like 48 bits, basically you just chunk to little 8s. You just do the little 8s independently, and you do a vector XOR of all the results because it's permutation. So I was kind of wow when we saw it in the code. It's like it's beautiful. Our compiler does that automatically. If you write your loop in a way, if you manually kind of break up the loop in a way that has small input bit width. So if you manually do the breaking up, the compiler is going to do the lookup stuff for you. So these guys must have spent months figuring this out, and we spent like a day because we knew what we were doing. Yeah.
Is it possible to have feedback loops in the network?
In the data channel, no. In the data path. So the data cannot be fed back to component processing. In the control channel, yes. For example, if you repeat, so you have a kind of a variable, and you update it in a computer, and then the computer finishes, and then you repeat the whole thing, then that's in effect a feedback loop in the control channel.
Why is that the case?
Sorry?
Why is that the case? I mean, when you do a simple thing like accumulate some stuff,
Yes.
you might need feedback loops. Why do you choose not to have data?
I don't know your concrete case that you have in your mind.
We can talk.
Yeah, we're gonna go with this. Yeah.
Any further questions? Let's thank the makers.